Hi, this is a video about the basic understanding of the atom we have today. This is very, very basic. It's probably stuff you know from a middle school or a high school chemistry class. By the way, I'm following the order of chemistry, the central science, by Brown, LeMay, Burston, and Murphy. This is the third section of their second chapter. Okay, so in a previous video, I talked about Dalton and how he revived the idea of an atom from the ancient Greeks. And then in another previous video, I talked a little bit about how Thomson discovered the electron, how Rutherford discovered that there's a nucleus. I briefly mentioned that Chadwick discovered the neutron and so forth. But now let's sit back and talk about the basic conception of the atom today. So this is a very badly drawn approximate version of what we might call the Niels Bohr model. It's a solar system model. He basically saw there being a nucleus and then there being kind of orbits in which an electron could be. And an electron could, if you excite an electron, you give it a little energy, you give it a Snickers bar, the electron jumps from one level to the next level. So here I've drawn kind of this is a very middle school picture of an atom. Bohr was wrong on some things, and as you get further into this chemistry experiment, you'll hear about s orbitals and p orbitals and d orbitals and f orbitals and things like that. So the atom doesn't really look like this, but this is kind of where we left off in the last video in the early 1900s. This kind of idea, the solar system model of the universe. So let's talk about the elements of the atom. You probably have already heard a lot of this somewhere before, but let's go ahead and cover it to get it on the page as we move forward through chemistry. So we talk of there being three particles in the atom. As it turns out, there are lots of particles, but this will get us going. Three particles: the electron, which is the negative charge. I don't know what positive and negative actually means, but you know that when I'm jumping my car and I put the leads on the wrong part of the battery, obviously there's a charge thing going on. We talk about positive charge and a negative charge. And if you're jumping a car, you want to make sure that the red lead is on the red post and that the black lead is on the black post. So the electron has a negative charge in the atom. As it turns out, it's more of a probability cloud. The electron isn't really in any one place. If you try to measure where the electron is, it'll show up in a place. But before you try to measure it, it's there's a probability of where that charge is and where that charge is distributed. Anyway, that's more advanced. If you want to think of an electron as a planet going around the sun, for now, that'll work. The proton, of course, is the positive charge. It's in the nucleus. So the electron is orbiting, as it were, around the nucleus like planets, and the proton is in the center, in the nucleus. Okay, this is where the atomic number comes from. How do you know what atom you're looking at? The number of protons tells you what atom you're looking at. So if there's only one proton in the nucleus, you're looking at hydrogen. If there are two protons in the nucleus, you're looking at helium. If there are three protons in the nucleus, you're looking at lithium, and so forth. The Bohr model here, this is not the way we really are, but there are 5 protons allegedly in that nucleus and 5 neutrons, but the 5 protons tell you that this would be nitrogen. Again, badly, not the way exactly it is, but it gets us going. So the positive charge in the nucleus is the proton, and the number of protons tells us what the element is. The neutron, of course, has no charge. You've heard the joke, maybe. A neutron walks into a bar and orders a drink, and when he's done, he asks the bartender how much it costs, and the bartender says, "For you, no charge." So that's the neutron. In this section, it mentions the idea of isotopes. So an isotope of an element is a version of that element with different numbers of neutrons. So the proton tells you what element is. So take uranium. Uranium, now let's go with something simpler. Take carbon. So carbon is atomic number 6 because carbon has 6 protons. Anytime you see something that's carbon, it has 6 protons. However, there are different variations of carbon in terms of the number of neutrons. So there's what we call carbon-12, that's the most stable version. Carbon-12 has 6 protons and 6 neutrons. But there's also something called carbon-14, which is a little bit radioactive. And so carbon-14 has 6 protons because it's carbon, but it has 8 neutrons. So you can see that these are called 2 different isotopes of carbon, one of which has 6 neutrons and one of which has 8 neutrons. So you can have different number, you can have the same element but different versions of it because there are different neutrons. The total number, you know, carbon-14, carbon-12, this is the total number of particles in the nucleus. We call this the mass number. The mass number is the total number of protons and neutrons in the nucleus. And so uranium-238 is very stable. It has, I don't remember the atomic number of uranium. Maybe I can pull it up real quick. It's 92. Okay, so uranium always has 92 protons in its nucleus. But it can have various numbers of neutrons. And so uranium-238 is 92 plus however many neutrons it takes to get to 238 particles in the nucleus. Uranium-238 is stable. However, uranium-235 with 3 less neutrons is unstable. It's radioactive, it deteriorates into lead over time, and it's what was used in the original atomic bomb. And so the atomic bomb that was dropped on Hiroshima and Nagasaki, that bomb used uranium-235 to start a chain reaction of disintegration, which of course, boom. So the mass number is based on the total number of particles in the nucleus, protons plus neutrons. Okay, this is the way we write it. It's not written very well here, I'm sorry. The C should be the same. The C should be right next to the 12 and the 6. It's up a little because I don't know how to do stuff. But this is the way you write it, right? C stands for carbon. The number on the bottom, so normally it would be right here at the bottom of the C, tells you the atomic number. So there are 6 protons in carbon. And then the top number, which is above the atomic number, this is the mass number, which tells you the total number of particles in the nucleus. And so this is carbon-12 we're looking at here. If it was carbon-14, there would be 2 extra neutrons, and it would be a 14 up here, but it would still be a 6 because it's carbon. Okay, not too hard. So some details to end up this video. The mass of 1 proton is roughly, or the mass of 1 neutron. So a neutron and a proton are about the same mass. A neutron is just slightly more mass than a proton. It's almost like if you took the mass of a proton and you added to it the mass of an electron, you'd get a neutron. That's kind of, so the mass of a neutron is just a little bit more than the mass of a proton. But we basically, for all intents and purposes, for lay people like me, we can say that 1 atomic mass unit, or that is 1 AMU, is roughly the mass of a proton, or roughly the mass of a neutron. Not exactly, because it's actually a little bit more. Mass of a proton is just a little bit more than an AMU. But we can get you started. Let's think of the mass of a proton or the mass of a neutron as 1 AMU. And that's real small. 1.66 times 10 to the negative 24 grams-ish, I'm approximating. So it's really small. But you know, it wouldn't be very helpful to use grams when we're talking about the mass of an electron, because it's really small. By the way, this is how much more massive a proton is than an electron. It would take about 1,836 electrons, the mass of that many electrons, to reach the mass of a proton. So a proton is massive compared to an electron, which is tiny in terms of mass. The charge on an electron is 1.6 times 10 to the negative 19 coulombs. You don't need to know what a coulomb is today, but a coulomb is a unit of charge. And of course, the charge on a proton is the same, except it's positive. Even though there's a huge mass differential between a proton and an electron, the charge differential is simply negative and positive. Same charge, just the proton's positive, the electron is negative. Lastly, it wouldn't do very well to use meters to measure things on the atomic level, and so there's a unit called the angstrom, which is, you can see the halo on the A. It's a very godly unit of measurement. So it's a unit of length that is 10 times 10 to the negative 10th meters. Well, that'll get us going. There is an introduction to the atom as we understand it today, although it gets really crazy when you go quantum. There you have it.